Hey everybody, it's Thursday, January 21st, and as you can see here in the aim today, our goal for today's video is all about how we can use conservation of energy to solve problems when friction is involved. Now, before we get to that, I want to take a couple of minutes here to finish the problems we were talking about yesterday on that worksheet that we started at the end of yesterday's video. So yesterday, we spent time looking at the problem on that worksheet on the front, which was all about sort of like proportional reasoning within a conservation of energy problem. On the back of the worksheet, there were two questions about work and power, and then another question, which I actually don't really want to totally solve, but just sort of give you a hint about just in case you see any of those kind of problems on a homework assignment. So let's just go ahead and get into it. The first problem I want to look at here is number 2 on the worksheet that was titled Work, Energy, Energy Conservation, and Power Problem Solving Worksheet. Yesterday we did number 1. Now we're going to the back and taking a look at number 2. This problem says student A lifts a 50 Newton box from the floor straight up to a height of 40 centimeters in 2 seconds. Student B lifts a 40 Newton box straight up from the floor to a height of 50 centimeters in 1 second. The question here says, compared to student A, student B does the same work but develops more power, the same work but develops less power, more work but develops less power, less work but develops more power. And of course, the question here says justify your answer. You do not actually need to do a calculation, as you can see on the actual worksheet, which I did not show in this question, or at least in this picture here on the slide, is that this question had lines for you to write an answer, so you do not actually have to calculate it. I want you to think about what the number should look like. And when you come up with an answer and an explanation, hit play, and we'll go over it. So the first thing that you need to know is that when you're lifting an object, unless they say otherwise, you should assume that the force used to do the lifting is equal to the magnitude of the weight of the box. And so here, the student A is going to be using a 50 Newton upward force, and student B is going to be using a 40 Newton upward force, because those forces will at least counter the weight of the object. And so the question here is, what is the work done by each student? The answer is, we don't care. We just need to compare them. And the key point here is, notice the numbers here for student A are 50 newtons and 40 centimeters, and the number for student B is 40 newtons and 50 centimeters. The main point of this problem, basically, is to get you to recognize that multiplication is commutative. And these numbers work out here pretty simply. First of all, joules are only obtained if the numbers you're multiplying are measured in units of newtons, and then the distance is measured in units of meters. And so basically the point of this problem was that 50 times 0.4 is the same number as 40 times 0.5. The work done by both students here is 20 joules. So student A and student B do the same amount of work because the product of the force and distance are equal to each other. So that allows us to eliminate choices 3 and 4 and now choose between choices 1 and 2. And the only other thing we really need to ask here is the answer 1 or 2? Is the power for student B, because notice it says compared to student A, student B does student B develop more power or develop less power? And according to the equation that we developed for power last week, power is equal to the change in energy over time. And what that tells us is that the power is inversely proportional to the time. Student B takes 1 second, whereas student A takes 2 seconds. And so the fact that student B takes less time, and the fact that these variables are inversely proportional, means student B develops more power, making the answer choice 1. A reasonable explanation to this question is going to look a little something like this. Work is proportional to the product of force and displacement, which is the same for both objects, so the students both do the same work. Additionally, We can say here that since power is inversely proportional to the time, less time means more power for student B. And that's it. Notice we've hit on all of the concepts in that question to get that the answer was choice 1 in 2 sentences. Take a second to pause this video here and write that down, adding any parts of this to your explanation that may be missing, or just writing down the whole thing if you kind of missed the mark on this one completely. And when you hit play, we'll take a look at number 3. Let's move on to part B of this question. Part B of this question says, now student A lifts the 50 Newton box from the floor diagonally, moving the box 40 centimeters to the right and 40 centimeters upward in the same 2 seconds. Compared to the work he or she did originally, did the student do more, less, or the same amount of work? Interesting question. I want you to take a second to pause this video here and think about it. I think the best sort of hint that I can give you to help you answer this question is, what is the work for? What is the work for? Take a second to pause this video here and think about this answer, and when you hit play, we'll go over it. Okay, so the key distinction here between these two situations is in the first part, the box starts down here and then ends up directly above it. That was the problem we already answered. In this particular situation here, the box starts like this, but then ends up over here. And instead of being 40 centimeters directly above its original location, the box is 40 centimeters this way and then 40 centimeters up. And the question here is, did the student do more, less, or the same amount of work? Now, a lot of people end up saying for this question, and this could have been some of you, so you should pay very close attention to this answer. A lot of people say for this question, the student did more work because the displacement of this box here now, if we're just going from center to center, is going to be the hypotenuse of this right triangle. And that's going to be more than 40 centimeters, the original displacement. And so that means the work done is greater because work is equal to force times displacement. If the displacement is bigger, then the work is going to be bigger. And that seems pretty obvious. The problem with that is that that answer makes a crucial error, a major oversight. And the major oversight was that we said when we were calculating the work originally that the force we were using in this calculation was equal to the weight of the box because the force of gravity acts straight down, and the applied force then to counter the weight of the box acts straight up. And if we were moving the object along this diagonal line here, that applied force, which is acting along this diagonal line, is not equal and opposite the weight. In fact, because the force we would be applying upward would have to be equal and opposite the weight, we would essentially have to use components to calculate the magnitude of the force in the direction of the displacement. Notice that this is the hypotenuse and this is the adjacent side, so it's going to go with the cosine. Isn't that convenient? But the point is, the fact that we have to account for the cosine of this angle means that the larger displacement doesn't matter because the cosine of the angle is going to be less than 1. And the exact amount the displacement is larger by, because this right triangle has these two legs, is going to be the exact amount the product of f delta x and the cosine of the angle are reduced because of the presence of that cosine theta. That's complicated, though. The answer is that it's the same work. My point in trying to help you with this question is that thinking about this answer in terms of the work equation is a mistake. The question I posed at the very beginning of you taking a moment to pause and think about the answer to this question was, what is the work for? The student is doing work to change the energy of the box. What kind of energy? Gravitational potential energy. And as we know, gravitational potential energy is dependent on the height change. and it has nothing to do with this change in the horizontal position of the box represented by this 40 centimeter leg of the triangle. The answer here is that the work is the same because the change in the box's gravitational potential energy is the same. And that's the point here. The work changes the gravitational potential energy. So since the change in gravitational potential energy is the same, the work done is the same. If you missed that, that's not so surprising. This question is kind of complicated. So take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, now we're actually going to directly move on to number 3 because it should be pretty clear to everybody that the time was the same, and now if we're saying the work is the same, the answer to part B is very straightforward. It's the same work, it's the same time, so it's the same power. That's pretty straightforward, though. I would imagine nobody has any questions about that. Obviously, if you do, feel free to reach out to me via email or comment, and I will address this point further. Having said that, because I want to get into the main focus for today, which is going to be about conservation of energy and friction, let's take a look at number 3. Number 3 here says a mass on a pendulum, which is attached to a string with a length of 3.4 meters, is raised at an angle of 43 degrees with respect to the vertical and released from rest. The question says to determine the speed of the bob, which is just the name of the mass on a pendulum, at the bottom of its path. Now, it's important to realize that when a pendulum, which is just a mass attached to a string, is hanging straight down, it's just going to sit there. When we raise it up, though, we give it gravitational potential energy. And the gravitational potential energy that this thing has here is converted to kinetic energy as the object swings down to the bottom. And so the point here that we're trying to make is very straightforward. And it's that this problem is a problem where the gravitational potential energy the object has in the beginning is converted to the kinetic energy at the end. Now, it shouldn't be that surprising that they're asking us for the speed at the bottom, and it shouldn't be much of a mystery as how we're going to go ahead and do that, because the kinetic energy equation is kinetic energy equals 1/2 mv squared, piece of cake. The complication of this problem comes in because they tell us here the angle to which the pendulum is raised and the length of the string. And we, according to the gravitational potential energy equation, need to determine the height. So we got a problem. The point of me showing you this problem is not for us to solve it, as I already mentioned, but it's just to talk about how we can find the height for this problem. The way that we're going to find the height for this pendulum, which we'll just write under the heading pendulum height, is by taking a look at the diagram, because I think if we take a look at the diagram, it'll become a little easier. So in its original state, the mass on the end of the string looks like this. When the pendulum is raised up at an angle, it looks like this. Simply taking the thing and moving it off to the side raises its height, where here they told us the angle is measured to the vertical, so here is theta. And the question that we are trying to answer once again is, what is the height? Now, it should be pretty clear to everybody. The height is going to be this value, right? The change in height is going to be the difference between where it is and where it was. Now, the obvious question here is, how do we figure that out? It's very important to point out 2 things. This measurement here is the length of the string. And even though these drawings are almost always exaggerated, this measurement is also the length of the string. The object is just being lifted up to the side. It doesn't actually shorten the string, right? And so it's important to realize here the way that we are going to find the height, delta y, is by using a little bit of trig. Because notice, by using a little bit of right triangle trigonometry, if we know that this is the length and we know that this is the angle, we can find this distance, which we'll just call x for the time being. And using a little bit of right triangle trigonometry, we can see that the length here is the hypotenuse of the triangle, and this distance that we've called x momentarily is the adjacent side of the triangle. And so if we have the hypotenuse and we're looking for the adjacent side, we're going to want to use the cosine of the angle. The cosine of the angle is the adjacent side, which we've called x, over the hypotenuse, which is L. And that means this distance x, this side of the triangle, is equal to L times the cosine of the angle. And so what we have here, and I'm just going to redraw the situation just to make it perfectly clear as to what we have here the length of the string over here. We have the length of the string over here. And this measurement from here to here being our delta y. And what we just found out is that this side of the triangle is equal to L cosine theta. And I hope everybody sees what we're now saying. If this from the center of the bob to the center of the bob is delta y, that's the same distance as this part over here, delta y. And what we're saying here is that this whole distance L from here to here has two parts, delta y and L cosine theta. So we can say L is equal to delta y, the thing we're looking for, plus L cosine theta. And so that means delta y is going to be equal to L minus L cosine theta. And that's it. Basically, for this problem, you take the gravitational potential energy and you set it equal to the kinetic energy. Like usual, you write mg delta y equals 1/2 mv squared. You cancel your masses, of course. And the main thrust of this problem, what makes it different, is that for delta y, you just plug in L minus L cosine theta. And that's it. Now, sometimes I just want to point this out because I don't know what the heck I was thinking when I was a 17-year-old kid, but this used to really, really confuse me when I would see textbooks write it like this. I don't know. Some of you might be laughing at me because I was so bad at math when I was a kid. But the point is, all they really did in that second part of it is factor out the L. Notice if we redistribute it back, we just get L times 1, which is L, and then L times cosine theta, which is what we originally have. If you're one of these people who is looking at that and says like, oh yeah, I could see how that would be confusing, I appreciate your sympathy. If you're laughing at me for my inability to do basic math, then I also understand. But that's the idea. Both of those expressions are equivalent. You punch it in however you'd like. If you want to solve for it off to the side separately, you can do that too. And then you basically just treat it as a regular problem where the final speed is equal to 2g delta y. Either you're going to write v final equals the square root of 2g delta y, or you're going to write v final equals the square root of 2g L minus L cosine theta, or L times 1 minus cosine theta. Either way, it's the same thing. And that's it for our discussion of this problem. So take a second to pause this video here and make sure you have all this written down. And when you hit play, we'll talk about how friction factors into conservation of energy problems. The main focus of today's video, or at least of the rest of today's video, is to talk about how friction factors into conservation of energy problems. And the main thing we really want to make sure we have down are basic concepts for work and energy before we get into that. The first question we can ask here is, how can we describe the relationship between work and energy? Why is it important? As we already mentioned here, work is equal to the change in energy. And if you do work on an object, the result is that that object will experience a change in energy. That's the point. Pretty basic kind of relationship there. We can also ask, how can we describe the physical significance of the fact that energy is a conserved quantity? The physical significance of the fact that energy is a conserved quantity is that the initial amount always equals the final amount of energy. That's the definition of a quantity being conserved, is that whatever amount you have in the beginning is exactly equal to the amount that you have at the end. We can also ask here, how can we describe the general procedure when applying conservation of energy to a physical system? And that's basically just applying what the thing says. We take the initial amount of energy and we just set it equal to the final amount of energy and we go to town. We substitute in for the equations once we identify which type of energy is present in the beginning and which type of energy is present at the end, and so on and so forth. This last question here is very important, though. How can we describe situations in which the total energy of a system is not conserved? And as we mentioned, mechanical energy, which is just potential and kinetic energy, mechanical energy is conserved in the absence of external work. Notice that really connects pretty nicely with the first point that we said here, because external work, as we asked in this first question here, external work changes the magnitude of forces. And if we're saying that external work changes the size of a force, well, energy is going to be the same number always, unless external work changes the amount of energy. That's the basic point here. Work changes energy. Energy is conserved unless energy changes. And since work changes energy, energy is not conserved if there's work. That's really all that we're saying. Now, of course, that's relevant when it comes to discussing friction. And the main thing we need to do when we're talking about how friction comes into play is come up with some new definitions. And so this leads us to definitions known as the difference between a conservative force and a non-conservative force. As you can see here on the screen, a conservative force is a force which allows for energy to be conserved. Specifically, if work is done against that force, the work can be recovered as another form of energy. A pretty good example of this is gravity. Another good example of this is the spring force. The reason why we're saying that these forces are conservative forces is because if you do work against gravity by lifting up an object, that work basically can be recovered as another form of energy. You didn't just do that work and it's gone. You lifted up the box and you changed its energy, specifically its gravitational potential energy, and if you let the object go, that gravitational potential energy will turn into kinetic energy. Same thing for the spring force. If you take an object attached to the end of a spring and you compress the spring, thus doing work against the force that's exerted by the spring, that energy is stored as elastic potential energy. And when you let go of the spring will expand, and that energy will be converted into kinetic energy. So the basic idea here is that the force is allowing energy to be conserved basically by storing energy. And so what these two things have in common is they store energy. And so a force is conservative basically if you can do work against it but have that energy stored. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Now, of course, the exact opposite of a conservative force is what is known as a non-conservative force. And a non-conservative force is a force that is dissipative or randomly disperses the energy of the object upon which it acts. Friction is a perfect example of a non-conservative force. The easiest way to tell what's going on here is to just take your cell phone and very gently slide it across a table. You might be able to hear mine hitting my desk over the microphone. I'm sure you've all seen this. You take your cell phone, you give it a gentle toss across the table, and you see it slides to a stop. What's happening is that friction is acting on the object, and it's taking that kinetic energy, and it's spreading it throughout the table and all the surrounding air. It gets rid of that kinetic energy. Once the object loses its kinetic energy, the kinetic energy that you gave it by giving it that gentle toss and applying that force over some displacement, the energy is gone. And that's the key distinction. And so a big and important question we have to ask here is like, well, what happens to the energy? It's really just gone? No, it's not gone. That would be a violation of conservation of energy in general, because the total energy of the universe is constant too. It just manifests itself as a different form, and specifically, it turns that energy into heat. The point here, though, is that it violates the laws of thermodynamics for that energy to ever be recovered. So what I wrote here underneath that is that when friction turns heat into energy, the energy can never be recovered in a useful form. And that's why we say it's a non-conservative force. If you do work against friction by pushing an object on a surface where there's friction, none of the energy is stored. It just spreads it out throughout the room. It turns it into heat. Whereas if you do work against gravity, that energy is stored in the gravitational field. Or when you do work against the spring force, that energy is stored in the spring. And that's the distinction. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, one of the important reasons, and a lot of this gets into like higher level physics when you're doing calculus. This is when this really comes into play, but it is important to know for this class too, at least on a fundamental level, is that whether a force is conservative or not determines whether the exact path that's taken is important. And so what we'll just say here is we'll just lay it all out. What makes a conservative force conservative is that if the work is done against that force, if the work done against that force is the same no matter what the length of the path taken between the 2 points are. Notice we actually just solved a problem where we saw this. If you take a box and you lift it straight up versus taking that box and lifting it diagonally, the work done is the same. And that's because the path doesn't matter. The work done against that force is the same because gravity is a conservative force. However, a force is non-conservative, like friction, if the work done against that force is different along paths between the 2 points. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So it'll probably be a pretty easy way to understand this if we just take a look at a picture. And so here is a picture representing the lack of path dependence for the gravitational force. We say gravity is a conservative force because whether you lift the object along the green line or the blue line, the work done is the same. And that's because the gravitational potential energy changes by the same amount. On the other hand, friction is a non-conservative force because whether you move the object along the blue line or the gold line actually matters. Notice before, when we were talking about work equals F delta X cosine theta, we were saying that, well, for gravity, you're opposing the weight. So even if you lift the object along a diagonal line, now the force that you're using is not the weight, but it's actually F cosine theta. And so it changes. For friction, the path matters. According to this equation here, the work is proportional to the displacement. And so more displacement means more work because friction is always ripping that energy away, meaning you need to keep pushing more force, more displacement to get the object to go from A to B. That's the idea. Take a second to pause this video here and sketch those diagrams in your notebook. And when you hit play, we'll move on. Now, we're going to use all this to solve a couple of problems. But before we do that, there are just some general notes that we should write down about what we just said. The first thing we'll say here is since friction is non-conservative, the distance or the path length is actually what matters, not the displacement. We've always been saying force times displacement. That's true for conservative forces. When we are dealing with a non-conservative force like friction, and friction is really the only non-conservative force we're going to be looking at this year, the distance or the path length is what actually matters, not the displacement. That's a very important note. Since work done by friction reduces the energy of the object, we know that it should be negative. And this makes sense according to that work equation, because the force and the distance, or really the displacement, will be opposite, meaning the angle between the force and the displacement are going to be 180 degrees, and the cosine of 180 degrees is -1, making the work negative. So take a second to pause this video here and write that down, and when you hit play, we'll move on. And lastly, for one more quick note here before we move on, the fact that the force of friction acts opposite the direction of the motion suggests that the work should always be negative, which makes sense because the change in energy caused by friction results in a decrease of the object's energy. That's a super crucially important point, and you will see that come up again and again and again and again and again in the problems that we're going to solve. Take a second to pause this video here and write that down, and when you hit play, we'll take a look at a problem. All right, so here's the problem. This problem, notice, is in the work energy packet. It's on page 12, number 13. This problem says a 70 kilogram base runner begins his slide into second base when he is moving at a speed of 4.0 meters per second. The coefficient of friction between his clothes and earth is 0.70. He slides so that his speed is 0 just as he reaches the base. Part A says how much mechanical energy is lost due to friction acting on the runner. And B says how far does he slide. Now, obviously, the first thing that we're going to need to do here is we're going to write down a list of the knowns. But even before we do that, it's probably important to say a couple of things. The first thing we should say is between this problem that we're going to look at right here and the problems we're going to solve tomorrow, there are a lot of different ways that you can solve problems dealing with the work done by friction. In my view, you should tailor your approach to the problem in a way that makes the most sense to you. I am going to show both of them over the course of the next 2 days. And essentially, and I know this part you might not like, but essentially, you're going to need to do what's most comfortable for you. However, I'm pretty sure all of you will be able to figure that out as we go through these problems. So I wouldn't worry about it too much. All right, so the problem says here that this base runner is 70 kilograms. And they tell us here that the coefficient of kinetic friction is 0.70. It should be clear to everybody that because we are given the mass and not the weight, to calculate the friction force, we're going to need to find the weight. And so we're going to need little g. 9.81 is what we use in the honors class. In this class, we use 9.8. We also know here that the displacement, oh no, sorry, not the displacement, that's what they want to know. We know that the speed that this person initially has is 4.0 meters per second. And we also know that they stop when they get to second base, so the final is 0. And here we're looking for how far the person goes. How far do they slide? And we could say that that's D. We can mark it with a delta X. It doesn't really matter. Whatever is comfortable for you. We'll actually write D equals delta X. The reason why we're not going to go too nuts about this, I hope everybody realizes, the reason why we're not going to go too nuts about this is because in this instance, the magnitude of the displacement is the same number as the distance because the person is moving in a straight line. So it doesn't really matter what we use is the point, whether we use D or delta X. Okay. Part A says how much mechanical energy is lost during the slide. So the obvious question here is, well, what kind of mechanical energy is possessed by the kid? And the kind of mechanical energy that's possessed here is kinetic energy. And so we can say here that the initial kinetic energy is just going to be 1/2 mv0 squared. And so here, basic calculation, we just have 1/2 of 70 kilograms, which is 35. And then that's going to be multiplied by 4.0 meters per second, the whole thing squared, which is going to be 16. And so when you plug those numbers into your calculator and you do that math, you end up getting 560 joules. Now, of course, And a lot of you were doing this last week, like sort of finding the answer, but not really representing it as it should be represented. Part A did not say what is the initial kinetic energy of the kid. It said how much mechanical energy was lost. And the amount of mechanical energy lost, or in other words, the amount the energy changed by, is the work. And the work here is equal to delta K, which is K final minus K initial. And of course, because the final energy is 0, the work is just equal to the negative of the initial kinetic energy. And so that means the work here is negative 560 joules. And that's it for part A. Part B is asking how far does he slide? And I want everybody to realize one thing, and we'll write this note down when we're done with this problem, is that work done by friction or work done against friction, in either case, the math is the same. You use the work equation. And what we'll say here is that the work is equal to, and we'll write this for part B, F delta X cosine theta. Now, we can write here that the angle is 180 degrees. It's just going to introduce a negative sign. Notice that number is negative. However you really want to look at it, it doesn't matter. There are a lot of ways that you can go ahead and approach this problem. What we should probably just say here is that this negative is going to introduce a -1. And so we'll just write here the W equals negative of the force of friction times delta X. Now, notice we can go ahead and solve this equation for delta X, and that'll give us delta X equals W over negative of the force of friction. And obviously, because we've run out of room here, we're going to need to go ahead and continue this work on the next slide. And so we'll go ahead and write here just that last line over again, delta X equals W over negative of the force of friction. So delta X equals W over negative of the force of friction. And now we can make our substitutions. Delta X is going to be the work over negative mu mg. Notice here we're just substituting in the equation for the force of friction. And now we're in business. We have all those numbers. So delta X is going to equal W, which we found to be negative 560 joules. And then we're going to divide that by the coefficient of kinetic friction, which was 0.70, times the mass of the object, which was 70 kilograms. So 70 kilograms. And then, of course, we've got to put our 9.8 in there as well. And when you do that math, of course, making sure you have all the units and making sure you don't drop any of your negative signs. Notice here now these negative signs cancel out, and that's exactly what we wanted. You get here a displacement of 1.16 meters. And that's it. All right, here's my little post-production magic. I realized when I was editing this video, sorry guys, that the answer on the calculator is actually 1.166. So that would make this answer to 3 significant figures 1.17 meters. Sorry about that. And with that, that's it for today. Obviously, there's a ton more that we could possibly say about the force of friction and how that factors its way into conservation of energy problems. And we're going to get into that in great detail over the next couple of days, because this really is a very important concept. But with that, this video is already getting a little long, so we'll leave it there for today. Have a good one, everybody.